Air traffic control, ATC, is a service provided by ground-based air traffic controllers who direct aircraft on the ground and through controlled airspace. The primary purpose of ATC is to prevent collisions, organize and expedite the flow of air traffic, and provide information and other support for pilots. In some countries, ATC can also provide advisory services to aircraft in non-controlled airspace. Controllers monitor the location of aircraft in their assigned airspace using radar and communicate with pilots by radio. To prevent collisions, ATC enforces traffic separation rules, which ensure each aircraft maintains a minimum amount of empty space around it. ATC services are provided to all types of aircraft, including private, military, and commercial flights. Depending on the type of flight and the class of airspace, ATC may issue mandatory instructions or non-binding advisories, known as flight information in some countries. While pilots are required to obey all ATC instructions, the pilot in command of an aircraft always retains final authority for its safe operation. In an emergency, the pilot may deviate from ATC instructions to the extent required to maintain the safety of the aircraft. Weather conditions, such as thunderstorms, strong winds, and low visibility, can significantly affect air traffic control operations, leading to delays, diversions, and the need for alternate routing. Language. Pursuant to requirements of the International Civil Aviation Organization, ICAO, ATC operations are conducted either in the English language, or the local language used by the station on the ground. In practice, the native language for a region is used, however, English must be used upon request. In 1920, Croydon Airport near London, England, was the first airport in the world to introduce air traffic control. The aerodrome control tower was a wooden hut 15 feet, 5 meters, high with windows on all four sides. It was commissioned on February 25, 1920, and provided basic traffic, weather, and location information to pilots. In the United States, air traffic control developed 3 divisions. The first of several airmail radio stations, AMRS, was created in 1922, after World War I, when the U.S. Post Office began using techniques developed by the U.S. Army to direct and track the movements of reconnaissance aircraft. Over time, the AMRS morphed into flight service stations. Today's flight service stations do not issue control instructions, but provide pilots with many other flight-related informational services. They do relay control instructions from ATC in areas where flight service is the only facility with radio or phone coverage. The first airport traffic control tower, regulating arrivals, departures, and surface movement of aircraft in the U.S. at a specific airport, opened in Cleveland in 1930. Approach and departure control facilities were created after adoption of radar in the 1950s to monitor and control the busy airspace around larger airports. The first Air Route Traffic Control Center, ARTC, which directs the movement of aircraft between departure and destination, was opened in Newark in 1935, followed in 1936 by Chicago and Cleveland. After the 1956 Grand Canyon mid-air collision, killing all 128 on board, the FAA was given the air traffic responsibility in the United States in 1958, and this was followed by other countries. In 1960, Britain, France, Germany, and the Benelux countries set up Eurocontrol, intending to merge their airspaces. The first and only attempt to pool controllers between countries is the Maastricht Upper Area Control Center, MUAC, founded in 1972 by Eurocontrol, and covering Belgium, Luxembourg, the Netherlands, and northwestern Germany. In 2001, the European Union, EU, aimed to create a single European sky, hoping to boost efficiency and gain economies of scale. In the USSR, the first air traffic control service was organized in 1929 on the Moscow-Irkutsk air route. In 1930, control areas were defined along all existing air routes. Airport Traffic Control Tower. The primary method of controlling the immediate airport environment is visual observation from the airport control tower. The tower is typically a tall, windowed structure, located within the airport grounds. The air traffic controllers, usually abbreviated controller, are responsible for separation and efficient movement of aircraft and vehicles operating on the taxiways and runways of the airport itself, and aircraft in the air near the airport, generally 5 to 10 nautical miles, 9 to 19 kilometers, 6 to 12 miles, depending on the airport procedures. A controller must carry out the job using the precise and effective application of rules and procedures. However, they need flexible adjustments according to differing circumstances, often under time pressure. In a study which compared stress in the general population and among staff working in this kind of system, there was markedly showed more stress level for controllers. This variation can be explained, at least in part, by the characteristics of the job. Remote and Virtual Tower, RVT, is a system based on air traffic controllers being located somewhere other than at the local airport tower, and still able to provide air traffic control services. Ground control, sometimes known as ground movement control, GMC, is responsible for the airport movement areas. Some busier airports have surface movement radar, SMR. Air control, known to pilots as tower or tower control, is responsible for the active runway surfaces. Flight data and clearance delivery. Clearance delivery is the position that issues route clearances to aircraft, typically before they commence taxiing. These clearances contain details of the route that the aircraft is expected to fly after departure. Analogous use. In the field of supply chain management, the concept of a supply chain control tower reflects the end-to-end visibility provided by an air traffic control tower. Ashutosh Gupta, writing for Gartner, observes that a supply chain control tower can be established by combining people, process, data, organization, and technology to improve visibility, control and decision-making. In the US, TRACONs are additionally designated by a 3-digit alphanumeric code. For example, the Chicago TRACON is designated C90. An area control center, as opposed to a terminal control center, is a specific type of air traffic control center that primarily controls IFR traffic, or aircraft at high altitude flying by instruments, instead of aircraft that are landing or taking off. Each area control center is assigned a flight information region, and certain area control centers near the coast are also tasked with monitoring aircraft flying over the ocean. Area control centers perform similar duties to other types of air traffic control, such as rerouting aircraft to deal with adverse conditions and directing the course of aircraft to ensure separation. Radar coverage. In the past, data on the position of aircraft were mainly determined by the following types of radar. En route radar with a coverage up to 240 nanometers 460 kilometers. Airport surveillance radar, with a coverage up to 52 nanometers 96 kilometers of the airport below an elevation of 25,000 feet. Surface movement radar with a coverage of the airport surface, within 2 nanometers 3.7 kilometers. Secondary surveillance radar with a coverage within line of sight range. In addition to such types of radar, some air navigation service providers, example Air Services Australia, the US Federal Aviation Administration, NAV Canada, etc., have implemented automatic dependent surveillance, broadcast, ADS-B, as part of their surveillance capability. This newer technology reverses the radar concept. Instead of radar finding a target by interrogating the transponder, the ADS-B equipped aircraft broadcasts a position report as determined by the navigation equipment on board the aircraft. ADS-C is another mode of automatic dependent surveillance, however ADS-C operates in the contract mode, where the aircraft reports a position, automatically or initiated by the pilot, based on a predetermined time interval. It is also possible for controllers to request more frequent reports to more quickly establish aircraft position for specific reasons. However, since the cost for each report is charged by the ADS service providers to the company operating the aircraft, More frequent reports are not commonly requested, except in emergency situations. ADC is significant, because it can be used where it is not possible to locate the infrastructure for a radar system, example over water. Computerized radar displays are now being designed to accept ADC inputs as part of their display. A radar archive system, RAS, keeps an electronic record of all radar information, preserving it for a few weeks. This information can be useful for search and rescue. When an aircraft has disappeared from radar screens, a controller can review the last radar returns from the aircraft to determine its likely position. For an example, see the crash report in the following citation. Problems. Traffic. Air traffic control errors occur when the separation, either vertical or horizontal, between airborne aircraft falls below the minimum prescribed separation set, for the domestic United States, by the U.S. Federal Aviation Administration. Separation minimums for terminal control areas, TCAS, around airports are lower than en route standards. Errors generally occur during periods following times of intense activity, when controllers tend to relax and overlook the presence of traffic and conditions that lead to loss of minimum separation. Weather. According to the Civil Air Navigation Services Organization, CANSO, weather significantly impacts global aviation, with more than 70% of air traffic delays being attributed to adverse weather conditions. These disruptions cause widespread delays, rerouting by ATC, and cancellations across continents. In 2024, Europe experienced a 40% increase in weather-related en route delays compared to 2023. As increasingly adverse weather intensifies the frequency and severity of these events, CANSO urged collaboration and real-time solutions among global aviation stakeholders to mitigate the effects of weather on flight operations. Infrastructure. Global ATC infrastructure is a complex network that varies significantly by region, with many countries facing challenges related to outdated technology, staffing shortages, and increasing traffic demand. While some regions, like parts of Europe and the US, have implemented modernization programs such as SESAR and NextGen, many others, especially in developing nations, still rely on legacy radar systems and voice-based communication, which limit efficiency and safety. These disparities contribute to delays and reduce the overall resilience of global air traffic management. According to the ICAO, coordinating ATC systems and accelerating digitalization is essential for meeting future aviation demands. Similarly, a 2024 report from the International Air Transport Association, IATA, emphasizes the urgency of investing in scalable, data-driven infrastructure to handle post-pandemic growth and ensure sustainability across the network. Congestion. Constrained control capacity and growing traffic lead to flight cancellation and delays. In America, delays caused by ATC grew by 69% between 2012 and 2017. ATC staffing issues were a major factor in congestion. By then the market for air traffic services was worth $14 billion. More efficient ATC could save 5 to 10% of aviation fuel by avoiding holding patterns and indirect airways. The military takes 80% of Chinese airspace, congesting the thin corridors open to airliners. The United Kingdom closes its military airspace only during military exercises. Call signs. A prerequisite to safe air traffic separation is the assignment and use of distinctive call signs. These are permanently allocated by ICAO on request, usually to scheduled flights, and some air forces and other military services for military flights. There are written call signs with a 2- or 3-letter combination followed by the flight number such as AAL 872 or VLG 1011. As such, they appear on flight plans and ATC radar labels. There are also the audio or radio telephony call signs used on the radio contact between pilots and air traffic control. These are not always identical to their written counterparts. An example of an audio call sign would be Speedbird 832, instead of the written BAW 832. This is used to reduce the chance of confusion between ATC and the aircraft. By default, the call sign for any other flight is the registration number, or tail number in US parlance, of the aircraft, such as N12345, CGABC, or ECIZD. The short radio telephony call signs for these tail numbers is the last three letters using the NATO phonetic alphabet, e.g. ABC, spoken Alpha Bravo Charlie for CGABC, or the last three numbers, e.g. 345 for N12345. In the United States, the prefix may be an aircraft type, model, or manufacturer in place of the first registration character. For example, N11842 could become Cessna 842. Technology. The Federal Aviation Administration, FAA, has spent over $3 billion on software, but a fully automated system is still yet to be achieved. In 2002, the United Kingdom commissioned a new Area Control Centre into service at the London Area Control Centre, LACC, at Swanwick in Hampshire, relieving a busy suburban centre at West Drayton in Middlesex, north of London Heathrow Airport. Software from Lockheed Martin predominates at the London Area Control Centre. However, the centre was initially troubled by software and communications problems causing delays and occasional shutdowns. Some tools are available in different domains to help the controller further. Flight Data Processing Systems. This is the system, usually one per center, that processes all the information related to the flight plan, typically in the time horizon from gate to gate, airport departure/arrival gates. It uses such processed information to invoke other flight plan related tools, such as e.g. medium-term conflict detection, MTCD. Short-term conflict alert, STCA, that checks possible conflicting trajectories in a time horizon of about 2 or 3 minutes, or even less in approach context, 35 seconds in the French Roissy and Orly approach centers. Center Tracking Automation System, CTAS, a suite of human-centered decision support tools developed by NASA Ames Research Center. Several of the CTAS tools have been field tested and transitioned to the FAA for operational evaluation and use. Some of the CTAS tools are Traffic Management Advisor, TMA, Passive Final Approach Spacing Tool, PFAST, Collaborative Arrival Planning, CAP, Direct2, D2, and Route Descent Advisor, EDA, and Multi-Center TMA. The software is running on Linux, MTCD and URET. In Europe, several MTCD tools are available: IFACTS, National Air Traffic Services, VFORIT, Deutsche Flugsicherung, New FDPS, Maastricht Upper Area Control. The Single European Sky ATM Research, SESR. The NAV Canada system known as expeditious. Screen content recording, hardware or software-based recording function which is part of most modern automation system, and that captures the screen content shown to the ATCO. Such recordings are used for a later replay together with audio recording for investigations and post-event analysis. Communication Navigation Surveillance/Air Traffic Management, CNS/ATM, systems are communications, navigation, and surveillance systems, employing digital technologies, including satellite systems, together with various levels of automation, applied in support of a seamless global air traffic management system. Proposed changes. In the United States, some alterations to traffic control procedures are being examined. Free flight is a developing air traffic control method that uses no centralized control, e.g. air traffic controllers. Instead, parts of airspace are reserved dynamically and automatically in a distributed way using computer communication to ensure the required separation between aircraft. In Europe, the Single European Sky ATM Research, SESR, program plans to develop new methods, technologies, procedures, and systems to accommodate future, 2020 and beyond, air traffic needs. In October 2018, European controller unions dismissed setting targets to improve ATC as a waste of time and effort, as new technology could cut costs for users but threaten their jobs. In April 2019, the EU called for a digital European sky, focusing on cutting costs by including a common digitization standard, and allowing controllers to move to where they are needed instead of merging national ATCs, as it would not solve all problems. Single air traffic control services in continent-sized America and China does not alleviate congestion. Eurocontrol tries to reduce delays by diverting flights to less busy routes. Flight paths across Europe were redesigned to accommodate the new airport in Istanbul, which opened in April, but the extra capacity will be absorbed by rising demand for air travel. Well-paid jobs in Western Europe could move east with cheaper labor. The average Spanish controller earned over €200,000 a year, over 7 times the country average salary, more than pilots, and at least 10 controllers were paid over €810,000, $1.1 million, a year in 2010. French controllers spent a cumulative 9 months on strike between 2004 and 2016. Many countries have also privatized or corporatized their air navigation service providers. There are several models that can be used for ATC service providers. The first is to have the ATC services be part of a government agency, as is currently the case in the United States. The problem with this model is that funding can be inconsistent, and can disrupt the development and operation of services. Sometimes funding can disappear when lawmakers cannot approve budgets in time. Both proponents and opponents of privatization recognize that stable funding is one of the major factors for successful upgrades of ATC infrastructure. Some of the funding issues include sequestration and politicization of projects. Proponents argue that moving ATC services to a private corporation could stabilize funding over the long term, which will result in more predictable planning and rollout of new technology as well as training of personnel. As of November 2024, the United States had 265 contractor towers that are staffed by private companies but administered by FAA through its FAA Contract Tower Program, which was established in 1982. These contract control towers cover 51% of all the federal air traffic control towers in the U.S. Another model is to have ATC services provided by a government corporation. This model is used in Germany, where funding is obtained through user fees. Yet another model is to have a for-profit corporation operate ATC services. This is the model used in the United Kingdom, but there have been several issues with the system there, including a large-scale failure in December 2014 which caused delays and cancellations and has been attributed to cost-cutting measures put in place by this corporation. In fact, earlier that year, the corporation owned by the German government won the bid to provide ATC services for Gatwick Airport in the United Kingdom. The last model, which is often the suggested model for the United States to transition to, is to have a non-profit organization that would handle ATC services as is used in Canada. The Canadian system is the one most often used as a model by proponents of privatization. Air traffic control privatization has been successful in Canada with the creation of NAV Canada, a private non-profit organization which has reduced costs, and has allowed new technologies to be deployed faster due to the elimination of much of the bureaucratic red tape. This has resulted in shorter flights and less fuel usage. It has also resulted in flights being safer due to new technology. NAV Canada is funded from fees that are collected from the airlines based on the weight of the aircraft and the distance flown. Air traffic control is operated by national governments with few exceptions. In the European Union, only Italy has private shareholders. Privatization does not guarantee lower prices. The profit margin of MUAC was 70% in 2017, as there is no competition, but governments could offer fixed terms concessions. The United States airspace is divided into 21 zones, centers, and each zone is divided into sectors. Also within each zone are portions of airspace, about 50 miles, 80 kilometers, in diameter, called TRACON, Terminal Radar Approach Control, airspaces. Within each TRACON airspace are a number of airports, each of which has its own airspace with a 5 miles, 8.0 kilometers, radius. FAA Control Tower Operators, CTO, Air traffic controllers use FAA Order 7110.65 as the authority for all procedures regarding air traffic. Thank you for watching this video.